What's up to you all, Matrix? This is Len Extra with me, AB and John. It is a Monday, a Triple M day. Mindset is Maths Monday, where you learn more and a Len Extra. John, how are you?
I'm really good. Grade 12 is great to be with you. Now, you may be confused. You might think it's a science show.
I was
it's
a bit
maths
confused
literature.
too.
Yeah, you're a bit confused, maybe. I know. But nothing much takes you to get you too confused. So I'm sorry about that one. But yeah, we're doing something that is really the most amazing tool of mathematics that has huge implications in physics. You know that? And so I thought that what we would do is we get a background to this in terms of how useful this particular topic is. And we use it all the time in physics. And even those of you that don't do some science and don't do physics, you're going to love using this particular tool called differential calculus.
No wonder why you're here, hey?
Absolutely. Had to jump in.
Awesome. Mindsetters, I hope you're all up and ready to learn more with us. All you need to do is to go to facebook.com/LearnExtra, like the page and join our Mindsetters, which are over 76,000. So make sure that you share the page, share everything that is on the page, and tell other Mindsetters to join us, but also help one another on the page. That is key because we are working together. On Twitter, we are at LearnExtra, so follow us also on that. But also, we've got something exciting for you guys, More Maths. All you need to do is to go to moremaths.org, and then you will register there and then join our South African group. You can test yourself there. It is a fun tool. John is going to show you guys how it looks like.
Okay, so guys, this is Nokia Mobile Maths. You don't just need to access it on your mobile phone. Yeah, you can access it on your mobile phone. And some of the service providers have made it available data free, but you'll have to check that out on the Facebook page. Once you've registered, you'll be able to choose which grade you're going to belong to and which group you want to belong to. Now, if you go to join group, I'm going to do that, and hopefully we'll get it going within a few seconds. You'll be able to invite yourself, use the code to the invite code that AB is going to post on the page, and join the grade 12 group. And there you see, I've got three groups going. This is the grade 12 group here that I've created, and I want you to come and join us. Because today we were able to send you messages, encouragement, give you notice of what's happening. And I just want to see, once you've joined the group, what you'll be able to see is where you rank within the group as well. So you can try and beat me, or you can try and beat your buddy, and you'll be able to get you'll be able to see who the members of the group are, who's at the top of the leaderboard, and let's see if you can knock me off the board there.
Look at you, John. You're just on top.
I'm just on top. I've only tried a few. So have a little bit of a competition. So if you're in that group, once you've joined the group, you can choose grade 12. And today we're dealing with calculus. So there we are. That's the group that you need to draw. And you'll see it breaks it down really nicely. Now, it's not just about doing questions. If you're stuck, there's some examples to follow through. There's some theory to read through. And it's really great revision. So you can see how far you can progress. And maybe in the future, AB, we might be having a few prizes for the people at the top of the leaderboard.
I like that. But for today, let's see who's going to take you out of the leading
Yeah,
part.
I want to see. Okay, can you get me out of the leaderboard? I'm sitting there at 250 points. Won't take much to move me. And you've got the advantage of it. The ad breaks, get on your phone, see if you can answer as many of these.
Cool. And your code for today is I2IK. I2IK. I hope it's simple, eh?
Yeah, that's simple.
I2IK.
And tell your friends. Get as many people as you know to really do some maths. And that's the important thing. It's for the fun of the maths as well. And you'll see it's great fun.
Awesome.
Okay, so for today, what we're dealing with is this topic called differential calculus. Now, historically, there was a huge debate about who actually invented it. The mathematicians and physics people have argued about it for a number of years. One person attributed to forming this rule of the calculus his name was Sir Isaac Newton. He's the guy that watched the apple falling and watched the moon going around the earth. And then there's a German fellow called Leibniz. And between them, there's been this intense debate about who actually started it, but we'll give them both credit this evening. So Newton and Leibniz, they were the ones that thought about developing this tool to solve interesting mathematical problems that were really more difficult to solve without the tool. And we'll come on to exactly what that is about. So to get to that stage, I want you to understand this evening what we're going to look at. We're going to explain the concept of a derivative, of a limit and a derivative. And then we're going to find derivatives of various functions. And then we're going to use differentiation, this process, this skill, this tool that Newton and Leibniz established to solve some practical problems. And because it's kind of a math science evening tonight, I thought we'd do the challenge question as a bit of a science question. But I'm going to make a proviso. You've got to use calculus principles to work this out, okay? So you can't just go and substitute and say, I know this because I've done it in grade 11 science. No, I want to put you all on a flat footing, even place here, and you've got to use calculus to be able to show the following. A ball is shot up into the air, and what I want you to tell you is the initial speed of the ball is 20 meters per second. They give you that the equation S is equal to Vt minus 5t squared, where S stands for the distance from the starting point, V the starting speed, and t the time describes the motion of the ball. So there we've got a nice equation that's describing the process of the board. And what we were asking you to do is to say, when will the ball reach its maximum height? Okay? And how fast will it be traveling at this time? So that's very, very, very important. And it's a really nice question. I wonder if you can solve it. But use principles of calculus to do that. Okay. Fair question?
It's fair, John.
Okay.
It's fair, and it's predictable because it's you.
Okay, absolutely. Thanks, Abby. Right, now let's get into the summary. Remember, we were going to start off by talking about this idea of a limit. Now, Abby, when we talk about a limit in everyday life, can you think of some limits?
Bank.
That's right. You can have a limit of the amount of money you can withdraw on a particular day. Right? So they put withdrawal limits. Another limit.
When you're traveling, like you have a limit where you can't go further than a certain distance, the end zone.
Okay, so there could be places that you can't get to. So it's kind of like a target point, okay? There's also the speed limit.
Yes.
So you should get close to the speed limit, but not actually go over it, okay? They want you to get there. Now, in maths, this word limit doesn't really have a similar meaning in some ways. What it's saying is the following. It says, let's take a very simple illustration. And I'm going to take a little graph here, and I'm going to just quickly sketch it for you, because I want you to get the idea of a limit quite clearly. And we're just going to use a straight line graph, and we're going to put some numbers to it. Very, very straightforward, okay? And we're going to say that point there has a coordinate of 0 and 5. Okay? And what we're going to say to ourselves is, what happens to the value of the graph as we get closer and closer to 0? So as I'm going along here, the x values, these are x values, and these are the y values. What happens to the y value as I get closer and closer to the 0 point? So I want you to see, if I chose an x about there, and I put it in, what's the y value going to be? Well, it's going to be that value up there. So that could be anything. It could be like something like 20, or it could be 15. I'm not sure exactly what it is. Let's just guess for the moment and say that point is 0, 20. Now, let's get a little bit closer to this one, and let's say we get to that point there. And at that point, it's 0 and 15. Sorry, it's not 0 and 15. I've made a mistake. This was the x value. I shouldn't have said 0. This is the x value, and it's giving me an output of 20. That x value is giving me an output of 15. So notice it wasn't a 0 that I'm inputting. I'm getting closer and closer to it though. As I'm getting closer to it on the x-axis, notice I'm coming down to this point on the y-axis. Now I could do that and I could carry on and I could say, well, this x, that was x1, this is x2, x3 brings me to the point where it's 10. Now it's still not very close, but I could blow it up and I could get closer and closer and closer and closer, and I could do it. I'm doing it from the right hand side here, getting the x's closer. I could do it from this side. So I could substitute in negative values and see what's happening. I could see, oh, there it's 0, here it's 1, or here it's 2, and over there, can you see it's squishing to a common point. So from above and from below, the values seem to be progressing to a number that sits in the middle, and that number is 5. Okay, and the reason we're saying that it's as we get closer to 0, the number approaches 5. If it was just a little bit short of 5 from above, it might be 4,998. If it get closer still, we could get it closer even on the other side. If it was below 0, like it was negative 0,0001, what would the value be? Well, it might be as little as 4,998. Okay, that's what that would be. On the top side, it would be 5,111. You can do this really nicely on a spreadsheet. But I hope you've got the idea that it's taking the x input and saying, what is the answer? What's the y value? What do we think it's going to be? What does it make sense to it? So let's go and read the definition now in words that I've written out. When finding the limit of a function, we look at what happens to the function value, the y value, as we get close to a specific x value on the graph. So our specific x value that we were looking at was x equals 0, and we were saying, what's the y value to that? Now, we will come across that a little later, and we'll show you some interesting problems. The most interesting problem is that we use this idea of a limit when we're looking at the gradient of a curve at a point. Now, I've said enough and almost too much that I want to just move on for a second. Remember in our little graph that we had there, and we had a Cartesian plane, and we had a straight line. Now, I'm going to draw a different straight line. I'm going to draw it through that point there, the 0, 0 point. So this is 0, 0, that point there, and let's make that point there, and I'm going to make this very easy. I'm going to make that point 5, 5. That's a straight line. Don't have to tell you that it's passing through the origin, and we can easily work out the gradient or the steepness of the line. Why would we want to do that? Well, because in some cases, gradient is quite useful. And there are many applications of working out gradients. And for straight lines, they tell us the identity of the equation. So we know that if we were to work out the gradient of a straight line, we would say, what are we going to do? We're going to say, take the change in y divided by the change in x. That means we take y2 minus y1 over x2 minus x1. And we substitute and we work it out. In this case, what you're going to do, if we take y2 as being 5 minus 0 over 5 minus 0, we'll get the gradient to be 1. And that's what we kind of expected because of the nature of the line. The gradient of this line and the equation of this line is y equals x. So we recognize the gradient is that number in front of the x. Now, that's all very well for straight lines, directly proportional relationships. But what happens if they're not exactly a straight line? What happens if we've got a phenomena that is a curve, a function that is a parabola or a cubic, and there are many natural things that follow this sort of shape. how are we going to work out gradient at a point? Well, that's exactly what calculus helps us do. Remember this formula. This formula we're going to use, okay, the gradient formula, but we're going to apply it to a curve. I want to just take that off for the minute and throw it away, because let's just take a picture now of a curve. And I want you to understand, if I've got something like a parabola, because a parabola is nice and easy, if I want to get the gradient, over here, I can't, the gradient's changing all the time. Notice, over here, if I took 2 points and I joined them together to get a gradient, what I would find is the straight line that goes through those 2 points kind of sits something like that. But if I took these 2 points, that point and that point, notice what will happen. The gradient will be different. The steepness of the line is different between those 2 points. But notice what I said. I don't want the gradient through 2 points, which is average gradient. I want the gradient at 1 point. And that's what calculus is all about. We, in fact, want the gradient of the tangent to the point. And I know I'm almost out of time, so I'm going to just finish this little thing, and then I'll come back to it. Okay, so what we want is the gradient of the tangent to that point. The gradient of the tangent to that specific point. Now, my graph isn't very good, but it touches at 1 point only. If we're going to find that gradient to the tangent, how are we going to do it? We're going to do it as follows. We're going to make this point, which we call point A, and that point B get closer and closer together. And we'll say they only have a small distance between them. The difference in x here, the difference in that x value we'll call h. Now let h get smaller and smaller so that those points A and B almost get on top of each other. So if h goes to 0, tends to 0, then we'll just use the change in y over the change in x. The change in x is h, and we're going to say let h equal 0. That's how we get the gradient of a tangent to a curve at a point. Very big terms there, but I hope that's helped.
I hope so too, and I think the mindsetters deserve a break, but it's not just any break, it is a working break.
Absolutely. Get on to MoMaths, get on to the challenge question. Let's see what you can do.
Well said. See you after the break. Welcome back, mindsetters. Now, the challenge question is on the page, and for the mindsetters such as Sibasha saying she's not even going to try it, just give it a try, mindsetter. I know that you are doing commercial subjects, but you can still give it a try because you are doing mathematics. It is about challenging yourself and saying you can still do it. It is a challenge after all, so it wouldn't just be a walkover. But otherwise, mindsetters, do check out the challenge question on the wall.
Okay, guys, I do hear you, and I am sympathetic to you. But you need to understand that you can get asked these questions in a maths paper about something moving. And I've given you a really simple equation. What I'm asking you to do is to find its maximum height and its speed at its maximum height. So think about it, and it's got more maths involved. The maths people, the people that do physics, I don't want to see any physics calculations. I want to see calculus. Application of calculus. Okay, now before the break we were talking about the gradient of the tangent to a curve. That's giving you the formula for 1 point. But the thing that a lot of people don't get is that I could have done it not just at this point. Let me choose a different color. I could have chosen that point, but I could have chosen that point, and I could have chosen. And in fact, I could have chosen that very turning point. I could have chosen all of these points. So if I do a table and I say to myself, let me take all the x values and let me take all the values of the gradient to the curve, I could list all of these, I could list all of those, and then I could draw a function. And in fact, we give this function a special name. We call that function the derivative. Okay. So understand that the function is the one that we start with, but then we do something to it to calculate the gradient at points along the function, and that develops into something called the derivative function. And so I want to just give you 2 bits of information about that. The formula for the derivative function, if we've got function f, then the derivative is written as f dashed x, okay? Or f primed x. I like to say f dashed x. The formula for getting f dashed x, you'll notice here, is the limit as h tends to 0, and what's this part? Any x, not just the point A, plus h, that little increment, minus f of x. So it's f of x plus h minus, that is just the same as delta y. Okay? And what have we got on the denominator? We've got the delta x. So we are finding the gradient. Now, I hope that's very clear. For the whole function, for all the points in the domain of f of x, all the points, we can get a corresponding function. Now, the notation that we use is that notation, f dash x. But there are other notations. We could have written it as y equals axn, ax to the n. Then we can write the derivative as y dash, or as, because it's a function of x, we write a capital D with a little x below it, or this one, which is quite popular, is dy by dx. So we say dy by dx, we know we're talking about the derivative. And we can then write it, what we're doing, dy by dx, or dy, or d by dx, and we could even put in brackets here f of x, something like that. This is saying to you, little delta, it's like the delta over here. It's asking what's the gradient. Now, the mystery behind this gradient story we'll unwrap a little. Why is it so powerful? Well, I'll give you a clue. It's got something to do with maximizing and minimizing, finding the maximum value, finding the minimum value. And that's why my question was, what's the maximum height that that ball can reach? See if you can apply these rules, and hopefully you'll get there. Now, we can do finding the derivative the long way, which is using that formula. We call that by first principles. And then there are some shorter rules where we can say that if we are given y equals x to the n, then we can write y dash or y prime as n x to the power of n minus 1. So you see what's happened? The power over there, we've subtracted 1, and we've created a coefficient of n over there like that. The sum rule is very important, and it's often not taught, and I want to emphasize this here. If we have 2 functions, and that could be something as simple as x squared plus x. We've joined them together. They're kind of, there's an additive point to them. Then what this rule says to us is you can take the function, whether it's plus or minus, and you can take the derivative of the first bit, so you can do that one, and then you can take the derivative of the second bit, and I'm going to move on there. The next one, which is important, is if something is a constant with respect to x, and we're taking dy by dx, then the y dashed, or y prime, is 0. Okay? The other important thing is if we take a constant multiplied by a function, then we can take that constant out of the derivative. We can find the derivative of the function, so you can factorize a common factor out, and you can then get just the derivative of the function. Please notice that this does not mean that you can take the product of 2 functions. Can't do that. Okay? There's a different rule which is not part of the grade 12 syllabus that's called the product rule, and there's even something called the chain rule, quotient rule. We're not going to do those at grade 12. They do exist, but doesn't mean it's the same thing. There's an added complication. So don't think that if you've got f of x times g of x, that you can just take the derivatives of each of them and multiply the derivatives together. It's not true, okay? You can't do that and then just say, well, that means if I start with that, I can take times g dash x. That's not true. They're not related, okay? You can't do that. I want to make that very clear. It doesn't mean that. You've got to be very careful of that. If you're given something as a product form, you've got to multiply it out so it becomes a sum or a difference between those. Right, I think it's time to get on to some questions. So the first question that we've got here is the question about going back to limits. And question about evaluating limits. And it's really quite straightforward up to a point, because I want to show you something. It's quite tricky. You've got to keep your wits about you. This first one, it says, evaluate this limit as x tends to 0, 5x minus 0. Well, in this case, all we're going to do is we're going to say, if I take 5 and I let x equal 0, then it's 5 times 0 minus 5 equals minus 5. So I would evaluate that by just substituting the 0 in and recognizing that it gets to minus 5. If I wanted to test it, I could take values a little bit before 0. So I could take like 5, 0, 1 or 0, 01 minus 5 and see what I'm going to get to. And it's quite a nice exercise in calculation. You'll get an answer here of a minus 4, 9, 9, ... Okay? Something like that. You could also take a number that's slightly bigger than a 0. So you could, or less than 0 at least. So you could take one that's slightly less than 0. You could take 0, 0, 0, 0, 1 minus 5, and then you're going to see that the answer here is going to be 5, 0, 0, 0, 1. It's slightly above, and they follow a trend. It makes sense that as we get closer and closer to 0, it converges to a number which is minus 5. Okay, that's the idea of a limit, and we should test it above and below. They don't always do that. It's sometimes just straightforward to see what it's looking like, except when you get something tricky like this. Now, as soon as you get, if we took away the limit, that's part of that. We didn't look at that. What would we know about this? Well, we would know immediately that x cannot be equal to 1. Can't be equal to 1. Why? Because dividing by 0 gives you an undefined answer. But what have they asked us? They've said evaluate what happens as x gets to minus 1. Now, strictly there is no answer to that. But in the limit, as it gets there, is there a possibility of us getting an answer of what it should be? What's the most likely value? Well, one of the things that we can do, fortunately, is we can do a little bit of algebra here. So we can say, in the limit, as x tends to 1, let's factorize x squared minus 1. I'm going to factorize it as x plus 1, x minus 1, and I'm going to put x minus 1 as the denominator. And look at that. That's quite cool. Because what do I recognize? That those two can cancel out. And now what I'm left with is the following. I've got the limit as x tends to 1 of x plus 1. So as x tends to 1, what's the limit going to be? Put 1 in place of x, and the limit tends to 2. Now, guys, this doesn't mean that 2 is the answer to this, to the value of the function at that point, because we can't divide by 0. But in the limit as x, the answer is 2. Because even with calculus, the derivative wouldn't exist because that h can't be 0 really. But in the limit, it tends to 2. The number that it's converging towards is 2. We check that out. Right. Now, the next question. Guys, this is a really important thing. And I've only got about 6 minutes to do it. So I want you to pay careful attention. You will get a question like this either in the June exam or the prelim exam and the final exam, or in all of them. There are a limited number of functions they can ask you to derive from first principles. But your setting out is crucial. And I'm going to go through your setting out, and I've chosen probably one of the most difficult ones to do. So it tells us to find the derivative of f of x, which is equal to 2 over x, from first principles. So the first thing I'm going to write down is what is f of x. And f of x is equal to 2 over x. What is f of x plus h? And I'm going to write this as 2 over x plus h. So now, what's my derivative? I want to find the derivative. Remember, the formula is on the data sheet. F dash x is equal to the limit as h tends to 0 of f dashed x, sorry, f, I mustn't put the dash in. Replace that for the minute. Just erase that part. There we go. F of x plus h minus f of x. And now that's the change in y. We're wanting the change in x. The change in x value is just going to be h. Okay? That's what we're looking at. And so now it becomes a little bit of an algebra problem, because all we've got to do is we've got to take this input and that input and put them into the equation. And we do that without forgetting in each line to write down the limit as h tends to 0. And I'm going to put that in now. So I'm going to say x plus h over 2 minus x, 2 over x, and at the bottom line h. Now, this is where you have to stay alert. In some cases, you're going to have to expand. And because there's a negative sign here, you need to make sure that everything on the right of that negative sign is applied to it. In this case, you've got a fraction. So how do we deal with fractions? And I'm going to take it very simply, and because I'm not as confident in some of this as some other people are, I'm going to take the common denominator. And I'm going to say to myself, x plus h times x is my common denominator. So how many times does this go? I'm going to say x plus h into the common denominator goes x times, 2 times x, and I will have a 2x on that side. And then on this side, I'm going to say minus 2. And how many times is x? It goes minus 2x plus h times. Now, please take note of that. I've got this all over h. So it's now getting a little bit messy because I've got denominator and numerator, and I haven't expanded. I'm going to expand the numerator, and we're going to see what it looks like. H tends to 0. Don't forget that. We're still letting that go. We've got h on the on the very bottom denominator. Then we're going to say 2x. Now, minus 2x minus 2h over x plus h, in brackets, x. It's still looking a bit messy. What am I going to do? What I've got to remember is the rule of tip and times. So what I really want to get to the point is cancelling out the h in the denominator. And that's exactly what I'm going to try and do right now. So recognize that this part needs to be divided into this whole thing. If I've got a fraction, think about that as h over 1. I'm going to tip and times, and I'm going to therefore write this as the limit as h tends to 0 And on the top line, I've got 2x minus 2x. Notice that 2x minus 2x, that can cancel. There's something that I can cancel out. I'm going to cancel it out. So be very careful. Look for those things that you can cancel. That can cancel with that. What am I left on the top line then? On the this very top line, minus 2h. And can you see what's happening? I invert minus 2h, x plus h times x, and times this by 1 over h. Now, look here. This is so exciting. I'm almost going to cry. Look what happens. Those cancel. And I can now write the next one. Limit as h tends to 0, and I've got minus 2 on the top line. I've got to expand on the denominator now. X times x is going to give me x squared plus x times h. Now, guys, please notice, it doesn't matter that I've got an h on it in the denominator. This h doesn't matter because it's with an x and there's another bit there that's going to keep me safe. So I'm no longer dividing by 0. I can simply say, right, I can evaluate it. I can now drop the limit. I can say let h equal 0. If h equals 0, what am I left with? Minus 2 over x squared. And that's the derivative function. Okay, make sure you've got it right. Take it slowly, take it step by step, but I think you've earned a break. Thanks, Andy.
Well done. Well, Mindsetters, after the break, so many things are happening. We'll be announcing last week's winner for the Casio calculator, so stay tuned for that, and also answering the challenge question, and lastly, taking some of your questions. So if you still have some questions, you've got these last few minutes. We'll see you after the break. Welcome back, Mindsetters. Now, the winner for our Casio calculator is Floyd. Congratulations to you, Floyd. This awesome Casio calculator is coming your way, probably sponsored by Casio. You still have got a chance, Mindsetters. Make sure that you answer the test yourself questions and send us the right answers to stand a chance. Otherwise, John?
Thanks, AB. I hope that Floyd, there aren't 10,000 Floyds. But just please remember, when you enter a competition and it says full name, then you need to give your full name, not just half a name, because, well, we've got your phone number.
But what if Floyd is the full name, John? You mean full name
like
and
Prince.
surname?
Yeah, like Prince or one of those. Yeah,
But-
okay. We're not
but the
all
former-
superstars yet, okay? Okay, Abby, you can go and practice your new name. I don't know what that's going to be. Okay, guys, there were a couple of questions during the break. We've done the most difficult part. We're going to be doing calculus for the next 2 weeks. 2 more shows of calculus, okay? But I'm only presenting the introductory. Next week, we'll move on to sketching cubics, and then we'll deal with applications of maxima and minima problems. But I want you to understand the foundations. Go back and look at them again. Deriving from first principles is essential. It's a guaranteed 5 to 6 marks on your final exam. So please don't get lost with it. It's very important. The example that we did with the 1 over x or 2 over x, you should be able to do the same thing with anything, any number over x. So you could do 5 over x and see if you get the right answer. So how do we get the right answer? Well, there's a short way of doing it, and that's using the short power rule and the sum rule. So I'm going to do a couple here because there were some people that were a little worried about it. So it says, when we normally ask you to find the derivatives of functions, we do it the shorthand way. So let's just do a, for example, and we're going to say we want f dash x. We're not going to go all the way through first principles. We're going to say the original thing said 3 times x to the power of 2. Now remember what it said. Take the power, subtract 1 from it. So 2 minus 1 is 1. Now take the index that was there and multiply it by the coefficient. So 2 times 3 is 6. Now, that would be fine. What we want to simplify it, though. What was the next term? Plus 8. But what do we know about any constant? Well, any constant is 0. So if we rewrite this, we're just going to say f dash x is 6x. Now, AB, you really can't get easy. I know some people say, oh, this is so difficult. No, guys, it's easy. Just follow the rules. And it's all about finding gradient. Let's do the next one, because I think that might also help us to follow through. So we're going to go to number B now, and we're going to say 4x cubed. We're going to call this y dash. And we're going to say, what's y dash? It's 4 times 3 is 12. X was cubed. It's now going to be squared. 3 minus 1 is 2. Plus the next one. And that's what the sum rule is just saying. If you've got one term, you can differentiate it. And then you can look at the next term and differentiate. So what's the next term? Half times x squared. We know that we must take the 2, multiply the 2 by half, and we get 1. So this is 2 multiplied by a half. And then we're going to go x to the power of 2 minus 1. We'll simplify that. Plus x to the power of 1. Remember, x on its own is x to the power of 1. Subtract 1, and we're going to get, this is 1 in the front, x to the 1 minus 1. Now let's just simplify those. We'll get 12x squared plus 2 times a half is 1, x to the power of 2 minus 1 is 1, so we can leave it as that, plus x to the 0 is 1. So we're just going to say that's 1. And there you go. Notice something interesting. We started off with a quadratic, and we've entered the derivative is a linear graph. When we started with a cubic, we've ended up with a quadratic. And that's a very important idea to get in your head. So by looking at the derivative, and a question that I had is question 4, we're not going to get time to do it, but go and have a look at it. It's really important that you can look at the graph of the derivative and you can read off the answers from that. Okay, last one that I'm going to do is I'm going to do this last one, number D. This one, okay, let's do number C and D. Sorry, it's just got too much. So, oh, I don't know why the board is playing up. It's not allowing me to see. So I'm just going to have to do it here. My tip for you, when you're given roots, write them as powers. So a root of, the square root of x is just x to the half, plus, now this is 1 over x to the half, but you can simplify that. You can write it as x to the half over plus x to the negative a half. And now you just apply the rules. So once you've got that, it's easy enough to apply the power rule. Now, this is the one that is the most important one, because it's minus x squared times x minus 2. Guys, you can't do anything with that on its own. You've got to expand it out, and then take the derivative of each step. Okay, I think it's time to look at the challenge question, because I know that there were some people that weren't happy with it. No, this is too much physics. Okay, so let's have a careful look. What we're told is we've got an equation. S is equal to negative 5t squared plus vt. Okay? And we're actually told what the v is. We're told the v is 20. So that was not too much of a trick. You just have to rewrite it as negative 5t squared plus 20t. Now, when you're given an equation like that, and you're asked to find maximum, okay, I want you to follow this very carefully. We did a little sketch earlier with the parabola, and we said the derivative is the thing that finds the gradient, okay? But what you should recognize is over here the gradient is negative, over here it's negative, and this white line, it's leaning the other way. So this gradient is positive, this gradient, exactly at the turning point. The line that is the tangent there, the yellow line, that has a horizontal gradient. So this point is either that's a minimum and that's a maximum. They have something in common. The gradient at minimum and max is equal to 0. So what we need to recognize is this is the power of calculus. We can maximize or minimize using the equation. And what we're really wanting now watch here, because this is another important thing. We haven't got x's here. We've got s's and t's. So we're wanting to find the derivative, the first derivative, ds by dt, okay? Because the output value for the function was an s standing for distance from the starting point, and t was the time. So now I'm going to find ds by dt, and I'm going to say, well, what is that? 2 times 5 is 10, t, plus 20. And notice that 1 has gone to the front, so 20 times 1, and that's got to 0. So there we've got a simple linear equation in t. And what do we need to do? We need to find when it's a maximum. We want to know at what time will it be a maximum. Have a look. It says, when will the ball reach its maximum? Now, this isn't a physics problem anymore. This is a maths problem, because we want the derivative function to be equal to 0, because we want it to be a maximum. So get it into your head. When the derivative is a maximum, then it's equal to 0. Okay? Sorry, not the derivative. When the function's a maximum, the derivative is equal to 0. Very important. So now we're just going to solve for it. We're going to say 10t is equal to negative 20, and we're going to find we've got a negative in front, and I've missed that negative, and I mustn't, because I don't want it to be a negative time. I can't have that. So t is equal to negative 20 divided by negative 10, and that's going to give me 2 seconds. Now you can check that this is right if you're a physics student, but it actually is a good approximation using this equation. The equation was the important thing, okay? The equation could have taken into measuring accounts and friction and all that. We weren't interested in that. We're not dealing with that at the moment. So now the next part is to say to ourselves, look at the question again. It said we've got the first part, when, and it says now, how fast will it be traveling at this time? Now, guys, so when will it reach the maximum height? We worked, how fast will it be traveling? This is an important point that you need to recognize. If it's reached its maximum height, its speed will be 0, okay? And there's a relationship here, and I'm going to stop just for a minute and say to you, the relationship between distance to speed to acceleration. If you take this equation and you find the derivative, the first derivative, you will get speed. And so what we're saying, at the maximum height, the speed is 0. And if we take the derivative of the speed equation, you will get the acceleration. Okay? This is either the derivative of that, and it's sometimes called the second derivative. Second derivative will give you the acceleration. Okay. We will have more to say about second derivatives next time when we're sketching cubics, but I hope for the moment that you can see that the speed or the time will be 2 seconds, And it was a little bit of a nasty to ask you what the speed was. I do acknowledge that. But I could have asked you what the height was, and perhaps that's what I should have done. Because to find the height, let me just move on from that and say, to find the height, what am I going to do? I'm going to say, so what is that height? So what's the maximum height? Height maximum, or S maximum, let me not use new notation. S maximum is going to be the original equation. What was the original equation? Let's go and look at it. It was minus, this board is really jumping, and I'm not sure why, minus 5t plus 20t. Minus 5t squared, sorry, minus 5t squared. So the maximum distance, or the maximum height that we're looking at, minus 5t squared, was it plus 20, AB? Plus 20, I think it is right, plus 20. And what we know is that the maximum height is going to happen when t is equal to 2 seconds. So we're going to say S of 2 is equal to minus 5, 2 squared, plus 20 times 2. This is giving us the maximum height. So 2 times 2 is 4. 4 times minus 5. 4 times minus 5 gives me minus 20. Plus 2 times 20 is 40. And it tells me that the maximum height is only 20 meters. I hope I've got that right. It does look right. 4 times 5 is 20. It looks absolutely right. So guys, I hope you've got that. I hope you've understood that. I hope you are comfortable with this idea of calculus. Maybe we've got a few seconds left.
Okay,
Are there
there's
any
a
questions?
that says there's a previous question that you've done where you said it was equal to minus 10, and he says, wasn't it supposed to be 10, not minus 10?
Where are we? I don't see which question was it.
Okay.
None of those had an answer of 10.
All right, let's
Minus 10, I can't see the minus 10. This was minus 10. No,
Yeah,
there's the minus. I did put the minus in.
He says it's 10, not...
No, the equation, look, very important then, let's just clarify. The given equation was minus 5t. Minus 5t. So when we say 2 times minus 5, we must get the derivative as being minus 10. Okay, I think that's about it.
Yeah, we've got about 20 seconds
Any
left.
others?
One other question that says, on question 1a, where did you get that minus 5? Question 1a.
Okay, let's go here.
And I
So
think you did explain that.
this one, the equation gives you 5x minus 5. So when we substitute a 0, we've
Unfortunately,
got
we're
the
out of time.
minus 5 is there. Okay.
Goodbye, my sisters.